All right, let's dive in. Today, we're going on a pretty incredible journey. It's a story that starts with something you use every single day, your phone's keyboard, and ends up somewhere you'd never expect, inside a hospital, helping to save lives. We're going to unpack how we taught computers to understand our language, starting from the absolute basics and building all the way up to the revolutionary tech that is changing medicine as we speak. So let's start right there. Ever type a text and your phone just knows what you're going to say next? It feels like magic, right? Well, it's not. It's the result of decades of work in teaching machines how to process language. And today, we're going to pull back the curtain and see exactly how it works, from the very first clumsy attempts to the super sophisticated models we have now. So, where did it all begin? Well, with a ridiculously simple idea called the bag of words model. I want you to literally imagine this. You take a sentence, you throw every single word into a big bag, shake it all up, and then you just count them. That's it. That is the entire model. Super simple, right? But as you can probably guess, it's got some major flaws. And this right here perfectly exposes the model's fatal flaw. Just look at these two sentences. The dog chased the cat, and the cat chased the dog. Now, to you and me, those are two completely different events. But to a bag of words model, they're identical. The bag has the exact same words with the exact same counts. The model has totally lost the meaning because it ignores the one thing that matters most, the order of the words. And losing the word order is just the tip of the iceberg. This model creates these gigantic, mostly empty lists of word counts. It has absolutely no idea what to do with a new word it's never seen before. And it definitely can't figure out that words like king and queen are related in a way that, say, king and cabbage are not. So yeah, we clearly needed a much better way. Okay, so the next huge leap forward came when we stopped treating words like these isolated little islands and started learning their meaning from their neighbors. This is the whole idea behind something called word-to-vec, and it's all built on one powerful hypothesis. You shall know a word by the company it keeps. And word-to-vec gets this done in two really clever ways. Over on the left, you've got skipgram. You give it a word, like love, and it learns to predict the words that are likely to be around it, like I and plain. Then on the right, you've got its opposite, CBOW, which stands for continuous bag of words. Here you do the reverse. You give it the context, I and playing, and it learns to predict that missing word in the middle, love. Both of these methods create these really rich numerical representations for words, finally giving the machine a real sense of context. But then the revolution happened. It was an architecture called the transformer. You see, all the older models had to read a sentence one word at a time, in sequence. The transformer was designed to read the entire sentence all at once. And this ability to process everything in parallel, it changed the game completely. The engine inside a transformer is just built different. It completely throws out that old one word at a time way of doing things. Instead, it processes all the words in parallel, using this incredibly powerful mechanism called multi-head attention to figure out the relationships between every single word simultaneously. Then it passes all that information through other layers to learn and make its predictions. But hang on a second. If it sees all the words at the same time, how does it solve that dog chases cat problem we saw earlier? Great question. The answer is something called positional encoding. Before the model even starts its work, it adds a unique mathematical signal. Think of it like a little fingerprint or a GPS coordinate to each word based on its exact position in the sentence. That way, even though it's processing everything at once, it always knows where each word came from. Now let's zoom in on the real magic behind the transformer, which is its ability to pay attention. This is the core mechanism, the secret sauce, that lets it understand all these complex relationships across a sentence, no matter how far apart the words are. At its heart, attention is really just a clever calculation. For every single word, the model creates three things: a query, a key, and a value. The query is like the word raising its hand and asking, hey, who in this sentence is important to me? It then compares itself to every other word's key to find a good match. The better the match, the higher the score. And those scores decide how much of each word's value, its meaning, gets blended into the final result. It's basically a system for creating a custom, context-aware definition for every single word. But why would you only want to look at a sentence from one perspective? That's the idea behind multi-head attention. Instead of just calculating attention once, the transformer does it many times, all in parallel. And each one of these parallel processes is called an attention head. This is the perfect way to think about it. With all these different heads, the model can analyze the sentence from tons of different angles at once. So you might have one head that's just tracking grammar, like subject-verb agreement. Another one is linking pronouns back to the person they're talking about. And maybe a third is tracking something like cause and effect. Together, they build a much richer, more complete understanding of the text. And the process itself is actually pretty straightforward. First, the initial input gets split up into multiple sets of those query, key, and value vectors we just talked about, one set for each head. Then, each head runs its own attention calculation, all independently and at the same time. Finally, all of their individual outputs are basically stitched back together and run through one last layer to produce the final result. So, transformers are amazing at understanding text that already exists. But what about writing new text? For that, we need one more clever trick: look-ahead masking. See, when a model is writing a sentence, it has to do it one word at a time. This mask basically puts blinders on the model, so it can't peek at the future words it's trying to predict. This forces it to make its next choice based only on what it's already written, which is absolutely crucial for generating text that actually makes sense. Okay, so we've just walked through how we built this incredibly powerful technology that can understand context and complex relationships in language. This ability to see the hidden connections between countless data points, well, that's exactly what you need to tackle one of the most complex systems there is, medicine. So the real question becomes, how do we take this power and apply it to actually saving lives? The big challenge in medicine is that you have data coming from thousands of different systems, all written by thousands of different people. To make any sense of that chaos, we don't just need to share data, we need to share meaning. And this brings us to a key concept: semantic interoperability. It's really the highest level of sharing data. It's about making sure that when one hospital system sends a patient's diagnosis to another, the receiving system understands it with the exact same clinical meaning. Without this, crucial, life-saving information can get lost in translation. A global standard called SNOMED-CT is designed to solve exactly this problem. It structures medical language in two main ways. On the left, you have pre-coordination. That's a single, predefined concept for a common diagnosis, like a heart attack. It's simple, it's direct. But on the right, that's where the real power is. It's called post-coordination. Here you can combine multiple concepts to describe something with way more detail, like specifying that a case of pneumonia was caused by a very specific type of bacteria. And this flexibility is everything. It's a total game changer. Post-coordination lets doctors document really complex or even brand new conditions with incredible precision. It makes the whole system scalable because you don't need to have a predefined code for every single possible combination of symptoms and causes. You can just build the exact description you need right on the fly. It's a true language for medicine. So there you have it, from a simple bag of words to a sophisticated, structured language that can describe the incredible complexity of human health. The journey of language processing shows this clear path from total chaos to deep context. And it really makes you wonder, now that we have this power to understand these intricate relationships and build meaning from data, what's next? What other complex systems, from financial markets to climate science, are we on the verge of decoding? Thanks for watching.